Hello, I'm Jim Handy, and I'm here to tell you about all of those new interface standards: OpenCAPI, CXL, GenZ, and C6. But first, a brief introduction for those who don't know me. I'm an industry analyst watching over the memory business. I work with two other very talented analysts at Objective Analysis to help our clients with their strategic planning in semiconductor and storage industries. We're really good at forecasting. I won't leave this up very long because that's not why you decided to watch this, but you can examine it carefully in the download. Every year we forecast the semiconductor business, and over time we have consistently produced the most accurate forecasts in the industry. In the download, you can click on the year for each line to see that year's video of me explaining the forecast. But you're here to learn about all those protocols, so let's stop talking about me. This is the outline of my presentation. I will first explain the problem in some depth before getting to all the solutions. Then I will present the choices for both far memory and near memory. After a summary, I will open the floor to a brief Q&A session. This slide is to show you where the problem originates. Lots of systems have two elements of roughly similar computing power. In many, it's the server and a GPU. But there are many systems that use special AI processors or other accelerators with large dedicated memories like the GPU. A server is made of a processor, a memory, and I/O. A GPU is made of a processor, memory, and I/O. They are very similar in that aspect. The server loads images from its own memory into the GPU's memory via a PCI bus, which is very fast, but which is much slower than memory access. It's kind of like a banquet. Although in today's pandemic banquets aren't being held, I am sure we all still have some fond memories. A key component of the banquet hall is the kitchen, which must serve a lot of food. Servers move the food from the kitchen to all of the tables. One sad day, someone decides to start a construction project between the kitchen and the storage room. The servers can still get food from the kitchen to the people in the banquet hall, but there are nearly 200 people in the ballroom who can't be rapidly served. The servers will need to take an alternate route out the fire exit, through the parking lot, and into another fire exit to the guests. This is slow, and the food is very likely to be cold by the time it arrives. This is similar to using PCIe to load the GPU's memory. So why not treat the GPU's memory as an extension of the processor's memory? Instead of the PCIe channel, why not allow the two processors to access each other's memory? It would accelerate the entire process of data sharing. This is the concept that motivated the creation of CXL, OpenCAPI, GenZ, and C6. Each processor still has a fast memory on its own board, which we will call near memory, and the somewhat slower access to remote memory on the other board, which is called far memory. The management of far memory is the goal of these standards. Perhaps the toughest issue is maintaining coherency. When one processor makes a change to a memory address, how does the other processor know that its own copy of that address contains the most current data? There must be some built-in responsibility for this. In an asymmetric system, one processor is responsible for this task. CXL, OpenCAPI, and GenZ all handle coherency this way. The alternative, called a symmetric system, allows all of the system's elements to share this responsibility. This is a faster, more robust solution that is used in the C6 standard. An asymmetric system is relatively simple to configure. Symmetric systems can be much more difficult. I could explain this in some depth since I wrote a book some years ago on cache memory design. We don't have time for that now, though, but I can share with you one of the illustrations from that book to give you an idea of the complexity involved and to let you know that some great minds already solved most of these problems decades ago. This system shows a very complex implementation of Future Bus Plus. The boxes show processors, cache memories, a standard memory at the very bottom, and a number of buses that communicate with each other through cache agents and memory agents depending on the direction of the data flow. A processor will look at a piece of data that it thinks is in the memory, but a more current copy might be in any of the caches in this diagram. The Future Bus Plus protocol assures that the processor will access the correct one. So even if the processor in the upper right side wants to access an address whose most current copy resides in the cache at the far left side of this diagram, it will be directed through a memory agent, then another memory agent, not to read the memory, but to go through a cache agent 1 to the upper left bus, where it will find the current data in cache 1-1.
This is an example of symmetric coherency.
So now that we know how coherency can be managed, let's look at other differences between these protocols. The top three are all based on pieces of the PCIe interface, the physical layer, the electrical systems used in the PCIe PHY, which is an extremely fast communication link and also bears similarities to the Ethernet protocol. IBM, the creator of OpenCAPI, used the OIF CEI 28G short-reach Ethernet standard PHY, which is similar to PCIe. GenZ was designed to solve a broader range of problems in supercomputers and can be used not only with PCIe, but also on Ethernet, optical data paths, or pretty much anything else. But these protocols cannot be mixed. They all use some standard number of lanes, but there's a lot of flexibility to allow designers to use more or fewer than these numbers. As I mentioned before, C6 is the only symmetric protocol, so the control column shows that control is shared for C6, while all of the asymmetric interfaces use centralized control. All of the interfaces support peer-to-peer communication, and all except OpenCAPI support switches, but these switches are incompatible with standard PCIe or Ethernet switches. OpenCAPI has a lower latency than the others by imposing this restriction. The transport layer received a lot of focus when these protocols were developed, but all use PCIe as a foundation except in cases where GenZ uses a non-PCIe base attached like Ethernet. One very unusual difference between OpenCAPI and the others is that addresses in OpenCAPI are mapped in the virtual address space, while in the others the addresses are mapped in the physical space. Careful bookkeeping is necessary with either approach. Probably the most important factor that will determine their acceptance, though, is support. All of these protocols are supported by leading processor and computer manufacturers. Most of them support 2 or more. I wasn't too thorough in putting together this list since there are so many supporters. What is most important is that Intel is heavily promoting CXL, AMD is behind C6, and IBM created OpenCAPI and then released it as an open specification to be shared with the industry. Aside from accelerating data movement between servers and GPUs, far memory interfaces will find other key uses. Server-to-server communications will be accelerated, and memory can be disaggregated so that it can be allocated in varying size slices to whichever server requires it. Very large memories can be made for programs that need larger memories than a processor can support. Finally, the processor doesn't need to be limited by the memory type that it was supposed to support. A processor that can only communicate with DDR4 could access DDR5 through one of these interfaces, or 3D XPoint, or another new memory like MRAM, resistive RAM, or FRAM. Even flash could be made available through a far memory bus. But speaking of new memories, I should mention that Tom Coughlin and I just released an update of our emerging memory report. Anyone with plans to use new memory technology should take a look at the link below. It's now available and can be purchased for immediate download using the link. One of these memory types that would be a good fit for the far memory interface is Intel's Optane DIMMs, which are based on 3D crosspoint memory. Today's version uses an extension of DDR4 that Intel calls DDRT. DDRT uses mostly standard DDR4 pins and adds a new DDRT-specific control pins that allow the processor to work with X points different memory speeds. This makes the bus complicated and proprietary. It also forces Intel to follow any changes to the DDR specifications. Those of you who are familiar with my company's memory storage hierarchy diagram might like to see where near memory and far memory fit. I added them to the left side of this chart. If you're unfamiliar with the chart, go to my blog, theSSDguy.com, and search for hierarchy. As I mentioned before, some of the protocols include more of the PCI interface or have more features, so they add latency to the far memory accesses, often in the order of 50 nanoseconds or more. This is satisfactory for 3D crosspoint and shared memory, but it's far too slow for near memory. So let's briefly discuss near memory. There are three basic interfaces that are suitable for near memory: DDR, HBM, and OMI. DDR is widely available and inexpensive. It can support pretty large memory sizes, and it solves most problems. The biggest issue with DDR is that it consumes a lot of power, and it requires a lot of processor pins to support. At very high speeds, additional channels are required, multiplying the high pin count requirement. HBM, or high bandwidth memory, is used in GPUs and other high-speed accelerators. It offers a very high bandwidth, but is costly and can only support low capacities. OMI is a development of the OpenCAPI standard, and it uses the same high-speed PCIe PHY that was mentioned before, with an otherwise memory-dedicated protocol. This adds only about 4 nanoseconds of latency when compared to a DDR4 LRDIMM. OMI supports near HBM bandwidth and larger capacities than DDR at low cost, low pin count, and low power consumption. There's a white paper about it on the Objective Analysis website. So that brings us to the end of the presentation. Here's a brief summary. For the best performance, memory should be treated as memory and not accessed through an I/O bus. CXL, OpenCAPI, C6, and GenZ all have done a good job of addressing coherency issues in far memory. There are also good alternatives for near memory: DDR, HBM, and OMI. Computer architecture will benefit from these advances. And with that, I'll be taking some questions from the audience.